I always advise everyone to go for space claim. Discovery has space claim inside, so it's the same thing. It's just a branding. And I will share the screen. Also, salutations to Alexandru. Привет. Привет, хороший человек, if I know some words. Nice meeting you, everyone. Let me remake the model, okay? So, what is this? No, this is another simulation. Here. Hopefully you can see the screen. Can you see the screen? Yes, you can see the screen. I promised you to do everything again. So let's start from scratch. Yes? Explicit dynamics. Firstly, a quick reminder about the cutter, how the profile looks like. Yeah, for the inserts. And we had the turning operations there, and you can see them here if they will expand. Yeah, facing, taper, whatever. This is mainly a function of the profile of the tool. Yes, and also the regime, let's say the feed, the velocity of the tool, or of the part, mainly of the part, because the part rotates here in turning. Let's also have a microphone here, even though it works also without expanding it. Okay, yes. Explicit dynamics. Double click on geometry. Now space claim opens. So I strongly don't advise beginners to use Design Modeler. It's very easy to use space claim. Let's make the workpiece. I said 50 millimeters diameter, and also let's make it something like an angular ring, 25. Also, let's cut it. With the tab, I will circle through the options, and I will make this 111. Okay. Escape. Trim operation, trim away. This is the workpiece. We will make this 3 millimeters thick, let's say, or 3.5. Now let's do the profile, the insert, let's say, yes. Let's model it. Design, sketch mode. We can rotate, by the way, the view. You see, we hover here, and we can drag this circle, yes. So the insert looks something like this. Trim. I can round this here, but I choose not to. Maybe I'll round it in the 3D. Let's move this surface that I just created somewhere. I'm just dragging the axis, yes. Something like here. And with we're going on design, tool, And I will click no merge, yes, in order not to fuse the bodies here. 5 is nice. All right. So triple click, 1, 2, 3, move, and yes, something like this, 2 millimeters. Perfect. Let's go even more outwards. Here we don't need it so much. Let's make this maybe 15 or 14, yes. This is the geometry. I said that I will leave it live edge. If we leave it live edge, we'll have a very nice mesh, very coarse hex mesh. If we round it, then we'll begin to have more elements and maybe get out from the hex meshing. All right, I don't want to save it here. I want to save the entire project. Save it. All right. I will leave space claim open in order to quickly insert it. In order to quickly insert the geometry when double clicking here, model. So what I did, I didn't do anything here because I remade the model from scratch. I prefer to go on explicit materials and add an explicit aluminum. Don't use linear materials when you are exceeding the large deformation domain, yes? Don't go here, don't choose here. Instead, go on either on general nonlinear materials or explicit materials. Double click. Now the model should load. Should I answer something else? No, sir, you don't share. Can anyone see anything? Now we have 2 spectators. Hopefully we'll catch their attention. As I said that I will chamfer this edge. So let me chamfer that edge, this one. Pull. We change to chamfer here. And I will do something like this in principle. Then I will lower this edge, yeah, this edge. Let me lower it a little, something like this. And this edge, let me make it something like this. Also, let's go to move, and I will move this bottom face. We don't need it so thick. Also, let's put the top face. Let's move it something like here. As I said, this is for principal purposes. We're here to learn how to do this simulation, so it's we don't need exact values. In your design, in your project, you will need to stay consistent with the dimensions that are required, so it's not the case at this moment. Maybe also move this. I would like to be very cheap and have an inexpensive model regarding the number of nodes and elements. All right, so let's save. And either from here or from here, we can right-click geometry, update geometry from source. So it loaded very fastly because space claim is opened. Let's now close space claim. Let's name what we have. This is the workpiece, and this is the tool. The workpiece is made of aluminum, and the tool I will make its behavior, its stiffness behavior as rigid. So at this moment, let's assign a cylindrical coordinate system here, because we'd like to assign the rotation of the workpiece. All right, so here I'm changing the Cartesian to cylindrical. How do we spell it? Cartesian. All right. So we have cylindrical instead of Cartesian. Body interactions, let's make this maybe frictional 0.2. What are we advised? Aluminum, steel, friction coefficient. How much should it be? Let's see. Steel graphite, come on. Why don't you give it? Oh. Static, sliding, long number runs. 0.6? Yeah, let's use 0.6, why not? Right-click generate mesh. Let's see how it looks like. It looks very coarse, to say the least. So, what we're looking at now, we're zooming the ruler in order to get a glimpse of the characteristic sizes, let's say. So 1, 0.5 or something. Here on the element size, I can write maybe 0.5, all right? If I keep this like this, maybe it will shave this top layer, all right? So instead, let's go and maybe have 0.4. Where the edge will touch, it will break, it will erode the entire row, yes? So we will surely erode these two top layers, all right? Let's even go further, and instead of 0.3, let's make it 0. All right, instead of 0.4, let's make it 0.3. I'm thinking about how hard will be for the workpiece to rotate. You know what? Let's move this even further down. Control B to select the body. Apply, and I will translate on y-axis with minus 0.3 maybe. No, 0.2. Oh, 0.1. All right. And on the z-axis, I will move it with minus 0.05 or 0.07. Right-click transform, and we will see the mesh. This is the mesh. Something like this. So in principle, the top 3 layers will be shaved in principle. I think the workpiece is too fine regarding the mesh. This is why I wanted to have an annular ring instead of a disk of a solid profile. Let's see how long will this simulation take, even though it's too fine for my taste. Let's assign some boundary conditions. Let me fix this, the tool, and I will rotate the part if it will work. Let's see if it works in this ANSYS version. I pressed Ctrl F to select faces, apply, and here instead of the global coordinate system, I will choose the one that I created. Look here, yes, this is the y-axis. It's not correct for our movement. This means we're going here and make the z the relative, axis, the particular z-axis. I will make it collinear to the global y-axis. The easiest way is to click here z and click here global y-axis. We will have a proper rotation. Yes, we want to rotate about this axis, the y-axis. Here we are on the coordinate system, and let's go. For sure, we will not have a displacement on the z-axis. We can make this 0. And for the y-axis, let's go on tabular. Yes, it works. We have degrees. You see here? We have degrees. What do we have? 3 steps. Why do we have 3 steps? You know what? Let's assign an end time. Maybe 0.001. And let's see from now on how the FEA will solve. Let's make this, in order to remove the red dots due to the mesh erosion, let's make this no. And output controls here 100 result number of points. This is a very important parameter. We'll leave it default at this moment. So let's assign some values. Why so many values? Of course, we need a minus, yes, in order to be opposite to this direction. The angle is 1 and 110. Let's make it 100. Yeah. So this should rotate here clockwise. All right, let's see what gives. Deformation, stress and strain, Control and Shift pressed, switch to automatic mode, solution information, deformation, come on. Solution, deformation, the velocity will be very high to say the least, strain and stress. We do have rotational velocity, you will see it after I have some results. Save. Number of cores 8, solve. Let's see how many days will take to solve with the default values. Clear generated data, solve. Do we have any message from the audience? A message which is not related to this topic. Singing fingers. Is it possible to extract the vibrational result of the tool, something like the oscillating graph of the tool, which is tool? Can you show how to do that? Now I fixed the tool, all right? If you have the tool, let's say with some degrees of freedom, you can plot some displacement, some deformations, even though they are very small, yes? So in principle, yes, but do not think as a model or something like this, because we are in explicit dynamics. We can plot some deformations, yes. You need to establish the axis on which you are going to evaluate, let's say, the small vibrations that appear. And yes, why not? Just apply a directional deformation on that axis. As we have, you imagine there will be a deformation on the piece only here because I fixed, and it's the same for the tool. You can assign a directional deformation and you will get the plots for the small displacements, let's say. What do we have here? We have 60 minutes. We like 60 minutes instead of days. Yes. Let's check a little on what our colleagues have performed. ANSYS machining, yes, machining. A femur on the machining. This is a nice try. Oh, let's see. I took inspiration from Mr. Foranzo Kefuka. He's we can call him an expert in such simulations and more. He has a very wide knowledge in simulations. So what have we here? Very nicely explained. Only he has some German here. Yes, because he not only studied in Germany, but I think he's established there. I know he made his PhD in Germany, I think. And this is why you can see some German naming here. Yes, so let's see. Den Ratenkorrektur, anfängliche Streckgrenzanspannung, Verfestigungskonstante, Querkontraktionsziel, I think, Dichte, density or something, Schmelztemperatur, the melting temperature, thermischer Entfestigungsexponent, or coefficient of thermal expansion, maybe. I'm just hoping to... so here is a very bidirectional, I can leave it default. Very nice tutorial. So I will not detail it because just for you to, when you have time for you to look on this, because it's very professional made, all right? He's not performing the FEA live. He's just saying about how it should be made, yes? The difference is that you are seeing now live results. Let's see here. Live, you'll see the simulation. In this case, you'll see the simulation from the beginning. Yeah, it's nice. It looks very nice. He's among the few ones that can do such simulations in ANSYS Workbench, or at least the few ones that published as I did. Also, his simulation here. Here, this is like a planing simulation made in 2D, I think, yes? Yes, it looks like it's made in 2D. A planing simulation made in plane with the surface elements. So the end time, the solving time kind of extended. And yes, we're on the right track. So now, because we're on the right track, and I don't want, nobody wants to wait 42 minutes at this moment, let's see how to decrease the solving time, yeah? So this is kind of like a template for me. So because the elements are pretty coarse, this is why they are broken like this. If we will refine the mesh, we'll have a very nice removal of the chip, of the metallic chip. Only the end time, the solving time, will increase very much. So let's close this and name it turning, which will act as a template. Duplicate. My goal is to maybe make it solved in around 15 minutes, if possible. So let's go here, and firstly, let's assign some mass scaling, all right? Automatic mass scaling, all right. And here, let's make it 7, just for fun. And here, 1, save. 1e minus 7, yes, the proposed timestamp. CFL is the acronym from the 3 mathematicians, Courant, Friedrichs, and Levy, from which lived around 100 years ago, if I remember correctly. Maximum sparse scaling 1. Let's save and solve. It stops here, so let me forcefully stop it. That will remake the solving. I think it kind of froze. This is the solver. We need to enter down. Clear generated data, yes, and solve. "10 minutes would be nice, but I think they will extend. 13 minutes, 14. Let's see how long it will go. My proposal would be not to exceed 20 minutes, but I think it will go on past half an hour, I think, yeah. So, this is some basic planing. Inspired from my first simulation. Cutting tool analysis. This I need to see. The mesh on the workpiece is very nice, very fine. Yeah, this is a milling, yes. It looks nice. But you can see, by the way, no legend, yeah? No legend, no results, only 30 seconds of, yeah. It's so hard to make a reliable and proper simulation, so this is why very few people dare to show some values, some legends, some results. So, contact stress, right? We don't need. This is also a milling that I have done in the past with 2D elements. An example of turning. This is what I would like to do today, yes? Something like this. Look here, the nodes, the inertia nodes of the mass centers of the eroded elements, yes? And I chose not to appear. And I think we can also see some temperature, I think. If it wasn't already shown. Yes, look here, some temperature. Around 90 or 100 degrees Celsius at the point of impact. Where are we going now? 36 minutes. Let's make it faster. Clear generated data, yes. And now, instead of 1e minus 7, can we ask for 1e minus 6? Save, solve. It will not work as it said in the beginning, because I have This one is nonlinear, so it will not have mass scaling applied. And this one is linear, only it's rigid, so there will be no mass scaling applied. So let's see what we can do to have a faster solving. 90 minutes, 20, 21. All right. So this is also a turning operation called beveling. Is it shown here? No. Yeah. So when you face a tube, I think it's called beveling. Yeah. It looks very nice. 26 minutes, 27, half an hour. Yeah, let's try and make it even faster. One proposal would be to make the annular portion, the annular ring, yeah, or the initial tube, to make it even thinner in order to save some meshing, to have fewer nodes. I was talking about this. No merge, and make it 17 here. Let's make it here 24. And this tool, let's make it something like this, 1. We don't care too much about the tool because it is rigid, so we don't care too much about it. Right-click, update geometry from source. Part transform, right-click transform. Let's see the meshing. $23,000. Before, I think we had about 30,000, maybe 35,000. Also, let's look on the boundary conditions. 0.1, fixed support, yes, and displacement. This is the displacement. What will happen if I apply the displacement here? Let's see. Solve. So now I think we should reach 20 minutes of solving. kind of a coarse mesh because I wanted to have fast solving. And when I'm using coarse mesh on my website and I sell tutorials and simulations with coarse meshing, is also to address I'm doing this to address the basic computing requirements, yes? Not everyone has lots of cores, all right? So also the licensing, yeah, maybe it's around 4 cores or 8 cores and not 64 or more cores. I'm talking about physical cores. In Explicit Dynamics, we should always assign the physical cores, not the logical cores. The logical cores are useful when doing CFD. This is a trial from Mr. Ahmad. Yeah, nice try. Okay. Our Japanese colleague, and this is one of my past simulations. I show it because it's pretty nice. Yeah, it was a lot of work and it's pretty nice. Let's see if it goes towards 20. Yeah, it goes towards 20 minutes. We're on the milling side, yes. I think again the tool is rigid and of course the workpiece is flexible and we have a proper meshing of the workpiece. It can be much finer, but yeah, we need a realistic solving time. Any questions from the audience? No? Perfect. This is one of my first trials. I'm a little ashamed to show it, but I said in parentheses trial. Also another trial. And I was in the beginning, and yeah, it's not useful at all, of course. Machining using ANSYS Workbench, part 2. Let's see. 27 minutes. Come on. You know, we will solve it for half, I think. Then we will stop the simulation because. Now I understand. This is why this displacement is not very useful, let's say. So when displacing only from this side, it's not very useful. It impedes, it decreases the stiffness of the workpiece, let's say. This is why I think we can leave it and also add this face with Control pressed, apply. Save and solve. You know, this on this side we don't need 3 elements. per thickness. I'm talking about this side, yes? So let's see if I can force to have one element per thickness, or maybe two. Let's see. So Control A to select edge, and this edge. All right. So let's see if it will work. And instead of element size, number of divisions, 1. Right click, generate mesh. Ooh. It kind of impedes with the, it collides with the 0.3 from here. Can I make here maybe hard and see if it will? Yes, with hard it works. All right. We have 14,000 nodes now. All right. Save. Clear generated data, solve. Of course, in reality, we need to correlate the feeding rate, yes, the process operations. Turning parameters calculator. For example, yes, we need to correlate this regarding the diameters, the layer that is going to be shaped, yes. This is the feed rate, which is like a pitch. And we need, in reality, to correlate all this when performing such a simulation, yes. I'm performing something very easy and quickly to understand, quick to solve. But yes, we need to have reliable parameters and give them correct results. So where were we? Here. Let's see. He defined a coordinate system for the tool. I'm wondering why. Body interaction. What? Frictionless. All right, frictionless. If you want it, even though the friction coefficient is so high, body sizing. Let's see the mesh. Generate mesh. Oh my god! Oh my god! It's so nice, but I'm curious about the solving time. So he's prescribing an initial velocity components, and he's using. So he created a coordinate system for the tool, and he's using global coordinate system. This means this coordinate system for the tool is redundant. 60 meters per second. So he's making a simple facing planing operation. And by the way, do you see? I don't know if you can see it. The arrow is pointing outwards because it's plus component. The arrow is outwards. Will he modify it? No. Why should he modify it? Oh my god! Oh my god! What can we learn from this? What? Okay. This is fixed. Displacement. What? What? You have an initial velocity. Why do you prescribe a displacement? I accept the only displacement I accept is 0z. Yeah? 0 on the z-axis. This is the only displacement that I accept. 0 on the y-axis. Yes, why not? And also on the z would have been nice. Let's leave it like this. All right. $5,000 seconds. Oh my God, 5,000 seconds. Oh no, please, no. He's talking maybe about erosion control. Maybe we don't have the subtitles. 90 minutes, yes, where we want. How does it behave? Oh, yes. It looks very nice. Come on. It's very nice, even though in the beginning there was something coarse here, but yeah. For something under 20 minutes of solving, it looks very nice. So let's go also on stress, because we're here. (0.5 geometric strain limit. Yeah, that is an important parameter. Cycles. All right, if you want it, all right. Solve. If he shows the solve, I don't know if he will show the solve. I think the solve should be a few thousand hours. But it's, yeah, does he show the solve? Let's see. How many thousands hours? I'm curious. With this mesh and this same time. Look here. It's so long that even the software says, hey, have patience, let me calculate. Oh my God. He's going for energy conservation. He finished. There is no result, ladies and gentlemen. There is no result. You cannot have a result with 5,000 seconds and this mesh. No, not in this century. And he has a part 1 and a part 2. Don't tell me he has a part 3. Please, come on. No, of course, no results. Mr. Laco, you're not teaching us. This is a beginner mistake. Very fine mesh and very big end time. So don't do it like he does it. What have we here? 21 minutes. I will run it for a little more and then stop it, because in principle it works. Or you know what? We can do this small trick. You know what? Let's half the end time. If we have half the end time, then here we'll have half the rotation, yes, the angle, yes. Let's leave it like this, no problem, because we want a very fast solving. Save and solve. We'll be satisfied with 10 minutes or 11, something like this. Clear generated data, solve. Again. So it will be in the end 10 minutes or 11. All right, a past simulation of mine, it's something in the beginning, let's say 10 years ago. It's not extraordinary, but it is something, okay? So this is my beginning, let's say, in the milling operation simulation. Yeah, it was something, one of my starting scenarios. This is made in LS-Dyna, but let's see. SPGI, I think it's a smooth particle Galerkin element, I think. Mr. Dennis Chan. Simulation is both my project and my hobby. I know too much. Also for me, it's also a passion. Professional passion. But yeah, these small SPH are like these ones. Like smooth particle hydrodynamics, yes? And instead, I think he uses the G's from Galerkin, I think. In ANSYS Workbench, we call them smooth particle hydrodynamics. Small spheres, yes? So here, this is made 10 months ago, and he has the material. We need to pay attention here. So now he's come on, what are you doing, Mr. Chen? Johnson Cook, all right. I think it's aluminum because he has here rho, which is density, and it's 2.7. Yeah, it's aluminum. Poisson ratio 0.3. And he assigned a Grunheisen equation of state with these parameters. This is the, I think it's bulk modulus or something, yes. This is the, Young's modulus, 70,000 megapascals, yes. All right, it's an aluminum. I think now we can, let's see what ANSYS version does he have. He doesn't show the ANSYS version, because in the recent ANSYS versions we can select also LS-Dyna materials. So he uses a default structural steel, then inserts a command to convert it to aluminum defined as in LS-Dyna. Okay. So body sizing, I'm curious to see where he defines the SPG mesh, let's say. So the mesh in principle is something like this, but it's not a small sphere, yes? Oops. He's defining a frictionless coefficient. I would have preferred frictional. Frictionless coefficient between these two bodies. All right. So 0.1 seconds. He could have made it even shorter. He's fixing, yes. All right. A velocity, yes. And what about this this portion? He needs to fixate somehow this portion of the piece with this portion. We need to have something like a bonded connection here or something. Section. All right. So here he is assigning the SPH, I think. Yes, SPH. One 1.5. Pseudo-Lagrangian. All right, and it will fail after it exceeds the plastic strain, and he assigns the plastic strain 0.4 as it can be assigned in here on the erosion controls. Here, it's something similar, let's say, to here, even though he uses plastic strain, not geometric strain, let's say. It's something similar. Are we on the right path here? Yes, we're on the right path. It's perfect, no, but we will leave it. It's very nice for this exercise. All right, so critical relative deformation. Yeah, he can. This is the geometric strain limit, I think, that we assign in ANSYS Workbench. Option of stabilization, simplified fluid particle approximation. All right. Self-contact indicator. No. It's important. The self-contact is important. If there will be like a coiling of the chips, then the coiling, the chips will touch each other. Yes, and this is important to have it, according to my opinion. If it will coil, but at this distance, it will not coil too much. Yes. I'm interested in how does he bond this part to this part. I'm interested. Default solver, control cards. Oh, commands again, commands. Default control, all right, and this. Yeah, this shows that this person knows LS Dyna. So this is the default time step factor, like a default time step factor. I meant to say this one. Time step safety factor. This is the default that it's used here. And here is, it's like a time step after the mass scaling, I think. Time step. Contact, penetration option, control energy, more viscosity, control solids. All right, yeah, this is LS Dyna kitchen. But yes, it's not for beginners. Come on, please assign a bonded contact somewhere. At least for me. Ah, he's jumping to... Yeah, so this simulation is made in LS Dyna that you see now. And he maybe attempts to remake it in ANSYS Workbench LS Dyna, let's say. In SPG, finite element nodes are converted to particles, yes. But I bet he will not show the simulation, the results in ANSYS LS Dyna, inside the ANSYS Workbench. I bet he will not show this, yeah. There is a lot to go. There is a long way to go from converting an LS Dyna simulation into ANSYS Workbench LS Dyna. It's a lot to go. So, does he have more? He has more. I am interested in having, let's say, ANSYS LS Dyna. Yes, ANSYS Workbench LS Dyna, not pure LS Dyna, which is complex, let's say, not user friendly, not beginner friendly, let's say. So he kind of showed the joints in LS Dyna, I think. Oh my god, it's so heavy, so complicated. Yeah, it's so complicated. This is why I didn't make so much LS Dyna simulations. I have some simulations here on this page in LS Dyna, but they are conversions, let's say. I made firstly I made these simulations, I made them in Explicit Dynamics, then converted them in LS Dyna. Yeah. All right, Mr. Chen. Let's see how many minutes we have. 3 minutes. 4 minutes. All right. So, do we have any question from the audience? We have a question. Please share a screen. Yes, is it possible? In terms of processor, should I choose a no processor with high number of cores, but lower speed, or newer one with fewer cores? Yes, but higher speed example. This is So firstly, it depends on how many cores you can use regarding the licensing. And at this moment, let's take an example, right? My case. I have 64 physical cores, around 3 gigabytes. If you can use all 64 cores, why not? Yes. Let's go for example, E7 to 969, just for fun. E5 to 969. Let's see what V4, let's say. Yeah? Let's see how many cores does it have. It has 22 at the base is 2.2, so it's not worth it. My advice for you is, if you can buy a Threadripper with maybe with 30 cores, maybe 32 cores, maybe. Yeah, 32 cores. And I think regarding the price, how much is the price? 32 price, all right? In dollars. Yeah, maybe a second hand, I don't know. Look here, yeah? But it's a gamble. It's a gamble, yes? And you advised another i7 13th generation. The problem is with Intel processors, they are very expensive. This is, you said i7, I think these ones. Let's make it a series 3. Yes, this one. What? Maximum total, of course. What is this? So these are the highest frequencies, I think. And is it worth to have? Let's make a small calculation. So something like this, yes. I will multiply 16 cores with 5, let's say 5 gigahertz. And this is around, I don't know, 80, maybe. 80 something. Yes. I will not call 80 hertz, 80 gigahertz, yes. I will call 80 something. And we can multiply 32 cores with, how much was this? 4.5, I don't know, maybe the base is 3.7, maybe the base, let's see. 3.7. $118.4 something, all right, it's not gigahertz, let's say. So definitely I would advise at least 32 cores, maybe second hand, I don't know. The price is kind of skyrocketed, so I don't know what to tell you. You know the problem with the RAM nowadays, and yes, somewhere in the middle, right? Perfect. It's solved here. Let me close space claim. And let's evaluate what we have here. Because I'd like to also go for the milling. Look here, I was talking about the self-contact, yes? I don't know if it took into account. Yes, it took the self-contact into account. Let me show you. You see, yeah. If I extend it a little, then you'll see that it took the self-contact into account. I would say this is a successful solve for the turning operation. Let's go for the milling now. What is the duration? 1.5 hours. All right. So let's do it freestyle and search for a mill. For a milling tool. All right. Delete here and do we use the same thing? Let's use the same thing. Duplicate and look for a mill. My intention is to kind of duplicate this simulation. This one, which will appear in a few seconds, hopefully. This is a very nice simulation. It's made with advent edge. This is very nice. Nirvana, pure Nirvana, yes. Yeah, it's dedicated to such machining simulation, so yeah. It was very easy, very quickly to set it up and solve it. Yes, this is dedicated advantage. Let's see, does it exist anymore? I think it exists anymore. It exists nowadays. 5 years. Yes, this is the original website. Oh, so nice with the fine meshing. It's so nice, this milling videos. Why? So they didn't publish in 2 years. They didn't publish any clip. Do we have one? This is, I think, it's like a CNC. Like a CNC, I think, model. But you know, I would say the market is kind of oversaturated with CNC. What is this? This is an example of what I've done, but I would like to start it, to make it from scratch. Yes, I was telling you about the fact that I would like to rig this simulation. Let me see. Yes, this one, which was in the trailer of this live stream. This is what I would like to perform now from zero. Let's hope that I am successful. Come on, show me. If I don't find a proper mill in the useful amount of time, I will use an existing geometry. We also have this option of modeling a mill, a rough tool. This is interesting. It's close to what I have in mind. I will take a look a little at my smartphone. Okay, now notification. Milling. Side milling cutter. Should we use this? Let's see. I have seen some rounds and I don't like these rounds. Let's attempt and download the file. I don't know if I can open it. Let's also download the cut part. I don't know if he uses a very recent Katya and SolidWorks, I think, and I don't know if I can download them. Let's see. Come on, let's go with the mill. What is this? So let me name this milling with a single N. Then double click geometry in order to model in space claim. This is milling, all right. We have a gear. Ah, this is nice. Come on. You know what? Let's choose here popular. Oh my god! Oh my god! All right. Do I have the geometry here? You know, let's see if I can open it. I have a pretty recent Altair, and this should be able to open these new geometry files. Ooh, this would be something useful, but it has inserts, and I don't want to have inserts. We would like to have the geometry as simple as possible. IGS. I think we will need to perform some healing. Let's like this. View all. Ooh. This is nice. This is nice, I think. Step. Yes, finally. It's download. Like. Let's leave it like this. Do we have something more? Something useful? All right. We were in space claim. For fun, can I open the recently acquired geometry discard part, for example? Can I open it? Yeah, let's save it as step, desktop step. And the next question will be if I can import that step into Space Claim, which is an older version of Space Claim. Let's see if it works. Oh, yes, it works. All right. Do I have an inclination? No, there is no inclination here. All right. Delete. Right-click, delete empty components. Mail. All right. So let's see if I can delete the rounds very easily. I click around one of the filets, selection, all rounds, delete. Yeah, click on the all rounds. Delete. Let's see if it goes as I wanted. Let's select again the rounds. Selection, all rounds, delete. Why should it work? Control Z. Let's firstly delete these rounds. Let's see if this helps. No. All right. Let's take it by hand. Delete. Come on, you're not going to give us problems. But you know what the problem is? There are too few teeth for my taste. So let's scrap this. Can I undo? No, not anymore. Let's open a tool with more teeth. All supported files. And we have here this this step. What is this step? What? Come on, why do you publish this thing? Why do you publish this useless thing? Open. So this is an IGS, and I told you that it might need some healing because I think it's made out of surface bodies. Yes. So it might need some healing. Look here. The first thing that I would like to do is there will be a lot of work. There will be. Let's see if I can delete this. No. Let's not complicate our lives too much. And let's go here. And use this. Let's save this geometry. So this is the geometry. It's very simple. Let's save it as milling. We can close this. Now we are in space claim. I can close space claim. And I will right click here, replace geometry, browse, desktop, milling. Let me double click in order to edit a little the geometry. We need to be original and have something extra. Any question from the audience? Hola, Mr. Cristobal. Hola, and congratulations on the new beginning for your country. Thank you for the nice words and good luck with everything. Yes. Thank you for the appreciations and good luck from me. No, you know I'm sincere and I want all the best to everyone. So we were here. Are we doing something similar with what we had? You know, let's pretend we're doing something original. Let's just pretend a little. Click here, and we have extrude edge, and we will extrude these edges just a little. Something like this. 4 millimeters. Then let's pull this with 2 millimeters. I was a little too anxious. All right, so let's drag these and have something like this, you know. Because we gained some elements here, let's shave a little here. 2.5. 2 millimeters. All right, so what can we do? What can we do? More. Let's leave it like this, all right? Save. And regarding the engineering data, let's choose also another material. Let's say general materials. Let's assign a nonlinear aluminum, yes, instead of what we had before. Let me delete here. Yes. And double click. It loads very quickly because space claim is open. F7 for zoom extents, all right? So let's close space claim for a while. And here, what do we assign? Will we have part transform? No, let's delete this. All right, and we have here the piece. And here is the tool, which we call it mill. Let's keep the tool flexible and make it structure steel. Let's keep it flexible at this moment. And the piece will be made of aluminum alloy nonlinear. Do I need a coordinate system? It can't hurt, all right? So Control F, something like this. It can't hurt, why not? Boundary interaction, we will keep this friction at 0.6. Edge sizing, I don't know. Let me right click and, oh my God. 100 millimeters, oh, it's pretty big. Let's make here 0. Sizing, let's make capture curvature no. Quality low. Right click, generate mesh. First question, you can see it's pretty coarse. First question, can I make this hex? Just asking, I don't know if it's possible. Yes, you can. All right, so instead of the usual 5 millimeters, can I have here 4 millimeters? Yes, we can. Let's look at the number of nodes. Even more. Can I ask for 3? I'm attempting to refine the mesh for the mill, because I will assign a very fine mesh here on the piece. Here now the mill looks nice. All right. So let's go here with how much should we go? Can we go with 1? Oh yes, oh yes. For faster solving. Can we go with 1.5? Yeah, let's see what this gives. And here, sorry, here I will assign, besides having the bottom, the bottom sides, besides having it fixed, let me assign maybe, let me delete this coordinate system, because I want to create 2 initial conditions, let's say, yes. One is the translational velocity, Control B, about the z-axis. We will go to the left, or now let's go to the positive z-axis on the right now. And how much should we go? How much? We will keep this, and we need to traverse around 50 millimeters. Let's see, around 50 millimeters. All right. So we will need to do something like this. The end time is 0.0005 seconds, and I will need to traverse, let's make 60 millimeters. Done. In 1 second, how many meters we will travel? Yes, x millimeters. So x equals 1 second multiplied with 60 millimeters. Always keep the measuring units, always. Over 0.0005 seconds. X is 60 over something. Let's not calculate too much. 60 over 5 seconds. This means we need to have 120,000 millimeters per second, yes? Look at the advantage of keeping the measurement units. This is what we're applying here. Yeah? 120 millimeters per second. Or 120,000. Yes? Look here, 120,000 millimeters per second. All right, but because it's... Should we dive deeper? Let's leave it like this. At this moment, let's leave it like this. And we are having this... let's also assign a rotation, because, yeah. The other initial condition is angular velocity. This is pretty straightforward. I'm wondering, I hope it is related, yes, and it is, I hope is related to the mass center. Vector, let's assign it here, how much? Let's assign a value, because I would like to, what? No, Control F for surface, and let's see if I, oh yes, perfect. And we would like to have the opposite side. Click again, click here, the black arrow, and it changed. Yes, it will bite, it will carve up from this piece. So let's provide, let's see some milling. Parameters calculators. Feed rate multiplier. Here we have some milling. Speeds and feeds. Rotations per minute. What I would like to get an RPM, rotational velocity. Average milling RPM, for example. Can you give me 100 for heavy steel cutting, 20,000. A common starting point for carbide in mild steel, 1,000 RPM. You know what? Let's think about 1,000 RPM. Yes. So can I assign here RPM? Yes. 1,000. Even though it's for steel and we are cutting aluminum, let's do it like this. I would like to see how many rotations we have. This means so we have 100 radians per second, but if we divide it again with 6.2, rotation is 6.2 radians, yes? 2 pi. 2 pi is 6.28. If we divide the 104 with 6.28, we will have the degrees, yes? So in a second is describing 16 rotations. You know where the problem is? The problem is this one, that we are using this timing. Yes? So let's make this calculation. In our case, seconds will be x angles. You'll understand in a second. So in 1 second, it describes 16 rotations. But how many rotations will be described in this amount of time? Yes. So x equals 16. Let's say rotation multiplied with 0.0005 seconds over 1 second. These are getting simplified and we will have rotations, yes? So x equals 16 multiplied with 0.0005. So we have approximately 0.008 rotations, which is not nice, yes? Using such a short end time, we don't have a full rotation, and I would like to have at least two free rotations. Yes? How do we do it? We need to increase the rotational speed, yes? Or increase the end time. I don't want to increase the end time because this means increasing the solving time. And we want live results, yes? So here, let's multiply this with something. So for 1000 RPM, we're not on the right path, yes? For 100 radians per second, we have this. Let's make it, I don't know, 10,000 RPM. If we make 10,000 RPM, we have 0. So for 10,000 RPM, we will have 0.08 rotations in this amount of time. Yeah. If we exaggerate to have 100,000 RPM, then we have 0.8 rotation. 1 second, please. I have an alarm. All right. 100 RPM would give 0.8 rotations. This would mean to have around 200,000. All right, so let's do something like this. Let's make this maybe 1. And let's make this you know what? Let's make this 0.01, and let's make this 50,000 RPM, yes? So 50,000 RPM would be 523 radians. If we divide 523 radians with 6.28, which is a rotation, then we have 83 rotations. Per second, 83 rotations per second. If we have 83 rotations per second, rotation in 1 second, how many rotations we will have in 0.01 seconds? Yes? X equals 83 multiplied with 0.01, and we will have 0.83 rotations. Yes? We'll have almost a full rotation. If we assign 5,000, but I mistook. I wanted to have 50,000. Yes, this means we have here 130, 130, and we have here 8 rotations, yes? Yeah, 8.3 rotations. Yes? So we need to make such calculations in order to ensure that we are somewhere needed, yes? This is 8 rotations. At this moment, let's not exaggerate, and maybe I said about 2 rotations, or maybe 3 rotations. This means instead of 50,000, let's divide it and let's make it 25. Yes, 25,000 RPM, and it's kind of in line with what they said here, that you can have I think for more rigid materials, I think you can have higher RPMs, if I'm not mistaken. All right, so this is kind of realistic, let's say. But I don't know, maybe we will need to decrease this. Save. This will ensure around 3 rotations or something, or maybe 4 rotations. Solve. Clear generated data, solve. And we have some mass scaling. Perfect. Let's increase here towards 50 maybe. Clear generated data, yes. Save and solve. How long will it take? 5 minutes. Yes, we agree with 5 minutes. Hopefully it will be something useful. Where were we? Here. All right. It's ANSYS milling. Let's see other trials. All right. Besides the nice stuff from Mr. Franz Kifuk, I think, Mr. Ahmad has made what? The real movie is not so much related with this one, but nevertheless, the simulation is nice. Here we have 268 megapascals. Yeah, it's a nice simulation. Another one. Yeah, nice. It's a little basic, but nice, yeah. Ahmad is performing nice FEA. What is here? 8 minutes. But are we on the right path? Let's see. It got out. Let's pause it because it flew away. So I have a very big velocity here. this velocity, angular velocity, it gets combined with this velocity. Let's make it a little slower. And let's ensure some depth. To ensure some depth, we need to incline this value, yes? With minus 10,000 millimeters. You saw? I inclined it a little, all right. So I will carve deeper, let's say. All right, let's see what will give with the new parameters. He's only moving the heat point, let's say. We looked already on this. ANSYS drilling simulation. I think you must be kidding because it's so hard to do a drilling simulation. He's making a drill in design modeler? I need to see this. Oh, very nice idea. I didn't. I'm usually choosing the easy way for space claim and grab card. Yes, we don't care about the model now. Let's go in ANSYS. What materials? Tungsten carbide. All right, can select such as yes, and just you're seeing just a poof. Yeah, poof. You can see for a second 600,000 Young's modulus. The density, yeah, this is correct. Carbon fiber reinforced polymer or something. Why? Aluminum alloy nonlinear. Material 1. 15.6. What? He's making another. All right. He has different plates with different materials, I think. Where are we? Oh. All right, let's hold our horses a little. Instead of 10 here, can we make 2? And here, instead of 10,000, can we make it 2,000? Here, for angular velocity. Let's make it 15,000 RPM, even 10,000. Clear generated data, yes. Save, solve. Of course, in a project, yes, in your simulations, you will revert to, you'll prefer the reliable values. Now we're just learning how to apply the boundary conditions and make the FEA work in a very quick, with a very short time, in a very quick computation. Clear generated data, solve. All right, so he has some carbon fiber plates. All right, I'm interested about the contacts. It's between the plates, bonded contacts. All right. He leads the default bonded direction frictionless. So I use low mesh first and then reduce the mesh size. All right. Low mesh means coarse. This is a killing mesh. This is not needed. Here maybe, but not here on the tool. Fix support. Yeah, let me see your boundary conditions. Remote displacement. Only on that face. Why? It can be if he has a rigid tool. Is his tool rigid? No, I don't think so. No, it's not rigid. So it's kind of a too small region to assign. Okay. Remote displacement and 0. All right, give me the rotation. About the y-axis, 5,400. How many rotations? 15 rotations. All right. But remember that someone should translate, either the tool, either the plates should translate. The plates will not translate because they are fixed, so he needs to also apply a rotation, translation, an axial translation. Y8, and it's not correct because it's on the outside. He does not see this. He made what rigid? He made the drill bit rigid. Why did you assign the tungsten if it's rigid? Rigid means infinite stiffness, so yeah. Yes, show me. $80 minutes, yes, 1 hour and 20 minutes. What is this? What is this? What is this? Come on, it's not useful. What is this? Come on. Oh, 30 minutes. Oh. We're going somewhere, even though we don't like it too much. Let's make a section view. Section plane, new section plane. Edit section plane. Yeah, I think I know what the problem is here, yeah? And the problem is, I think, something like this. Because the geometric strain is too much, it's, let's say, too kind of elongated. I would not say elastic, but it's too elongated. It's like a rubber or something. Let's go here on analysis settings and make here maybe half, 0.75. Also, the mesh is kind of coarse, but yes, let's see what it gives with the new geometrical strain limit. Kind of strain limit, yes. Oh, this should be interesting. With the flexible tool, you see the tool is, it wobbles, it's so flexible. I would like to do something similar, but with the entire tool and to have like an angular ring cut out. And yeah, I'd like to do something similar in the next simulations. Do we have any questions? No? Perfect. Our audience is increasing. It was 3 and now 2. 2 people watching. 2 students, 2 engineers. Okay. Ooh, yes. Yes, we're on the right side. Let's solve this, and I will duplicate. I will refine the mesh and solve it again. Does it get out or it's me? It gets out. It's getting out. Come on. Why do you get out? Yeah, it's no longer here. Let's stop and provide further inclination. here on the velocity, you see, this inclination is not enough. We need to go further. Should I make here 3? No. Instead, I should keep this 2 and make here maybe 4. Yeah, something like this. And a little more. I would like more RPM here. And the mesh. I said mesh. 1.5. I have 13,000 nodes, and now we have 22. Let's leave it like this. And maybe the usual mesh, I would like to also refine a little this mesh, a little. It's not much, but it's fine. All right. Save. Solve. Clear generated data. No, I want to, okay, it's correct. I was thinking maybe there was a mass scaling error, but no, it's not the case. Clear generated data, solve. Clear generating data, solve. Yes, we have some mass scaling error due to the refinement of the mesh. This means we are going here and instead of 50, can I make here 100? Save, solve. Solve again. Yes, solve. So this will maybe get extended to 15 or 20 minutes, maybe. Hello, Mr. Vasile. Interesting topic, a lot of learning. Thank you. Yes, thank you. Thank you again. Thank you, Mr. Vasile. It's basic. It's for beginners, and yes, in the future we can complicate them. No problem. It's very easy to complicate. The hardest is to keep things simple in the beginning. So So we were here. Oh, this looks so nice. What is this? Interference solid mesh. All right. Yes. This is nice. He's moving the workpiece. Yes, here he goes very deep into the calculation. He wants to correlate the measurement, the experience with the simulation. He does not show values because he's not content with the... Does it still work? Oh. Where was I? This looks nice. 1 second. Fast but correct, I would say, yes. Mr. Hamed, what did you do here? It's nothing. It's CAD-CAM with because it's not FEA with Hamed. It's CAD-CAM. So, Mr. Hamed, why are you showing this? It's a lateral milling, let's say. This is 2D, yes? It looks like 2D, yes. A million RPM. This needs to be seen. Oh my God, oh my God, oh my God. I think it could be correct. I'm looking at the end time and it could be correct. What is he showing here? 6 minutes, all right. And ooh, it's beginning to look a lot like Christmas. And we would need even a finer mesh in the piece. Let's leave it like this, and we'll close the live stream. No, it can be refined, no problem. Chrome kind of freezes. Come on, what is... he's showing the equations. And this is all... transient thermal FEA. Yeah, it could be. He's pretty shy in showing the values, and we can see here some 130 something, and then maybe decreasing. Yeah, it's not easy with the temperatures in ANSYS Dynamics. I was talking about ANSYS Dynamics, but he's doing transit thermal. All right, I'm no expert in thermal FEA, so yeah, I'm a beginner, so I will not comment too much. What is this? What is this? Come on, come on. Why? With a finer mesh on the piece, I think he would have been on the right path with the finer mesh, I think. Where are we? 70%? Yes. So. Nice. Very nice. Mr. Wilmer, let's see, what is this? Autodyne. Okay, all right. 13 years ago. He has SPH. He has small spheres, you see? Yeah, SPH. We cannot see it from above. Yeah, it would have been interesting to see it from above. SPH. I think also I will perform some machining with SPH with the small spheres. Let's see, expert FEA SPH, smooth particle hydrodynamics. So I have a breaking, I have this hydroplaning, some excavation, this karate chop, some sand here, but I don't have machining with SPH. I need to perform some machining with SPH. So nice simulations, a lot of work, years of work. 2.2. Are we on the right path? Yes. Again, it gets out. And because I didn't leave it rigid, it's simple steel, it gets chipped here, all right? So it's first time when I see a chipped tool, because usually we don't see a chipped tool, yes? The highest value is given by the chip, and the chip is very far away. This is why we need to have a different, let's say, a different deformation plot for the piece, for example. Look here. It's still too far. Can I make it just visible here, no. But what will happen if I cut here, change the direction, change direction to here, and here make it just visible. Does it work? No. Something like this, yes. Let's have a fully solved simulation, even though it's not very decent. How much is the time? We're in you know what, let's go towards 3 hours. Because I would like to optimize a little the simulation. So because it goes too deep, it kind of blocks here. It gets stuck, yes? So let's duplicate it. We duplicated the previous scenario. So let's go a little, not so much low, a little higher. Zero 0.03. What will happen when I make this rigid? So the tool is rigid now, yes? All right, 25,000 nodes. What if I make here 1.1? What is the difference? 29,000. All right. Let's solve. One minute. 1 minute is acceptable. But let's see how it looks like. kind of flies away. Yeah, the contact is too stiff, too rigid, let's say, and the mill is bouncing back. Let's make the material a little softer, let's say, yes. .5 here. We give the material the possibility to be broken even faster. And let's change the fixed support to these faces and save again. All right. Let's see if changing the stiffness to rigid, let's see if it works, because, okay. We need to see the mill dive deeper into the workpiece. I'm interested to see if it's out. Okay. Let's change the stiffness again, back to flexible, because it gives problems this approach. Due to the increased stiffness, it bounces back. Increased stiffness, the infinite stiffness of this being rigid, it bounces back. Also, this is pretty stiff due to the mesh density, which is very high. It's very fine. All right. "12 minutes. Oh. Because this mesh is very fine. Let's see if it keeps the trajectory. Judging from the plot here, we have a tendency to fly away. The red is up, so there is a tendency to fly upwards. Let's see. Now it's kind of stabilized. It's a uniform rotation, let's say. Does it cut out? Yes. Come on. We've seen a bouncing here. Yeah, I think we are on the right path. Let's see if we have LS dyna milling. This is very nice. He's a guru in LS dyna. I mean Topa. Ilyushkin Maxim. Oh, yes. Mr. Ilyushkin Maxim. Yes, we need to see his work. Yeah, this is Nirvana. It looks very nice. The stress is kind of low. I don't know why. Maybe the scale, the measurement unit is more than I thought initially. Yes, this is 2D, very nice, yes. Mr. Ilyushkin. We don't have, okay. Strain and, do we have stress? We have stress. Someone copied someone. Who copied who? He copied, yeah, because he, oh, no. He's the first, and Mr. Ilyushkin, no, Mr. Ilyushkin is first, 8 years ago, and he copied from Maxim. Yeah, this is my assumption, because he's the first to publish and with the same values, yeah. I think it's the same values. Nevertheless, someone copied someone. I would like to see his channel. So he's actual. Привет, Господи Максим, как дела? Привет. So he's actual, okay? He's not banned on the channel. Автоматизация создания расчетных файлов, припост, примеры, руки. Okay. So he's doing it, I think, from scratch, I think. Let's see. Yes, this looks promising. From scratch, yeah. Let's see the animation. It's so nice, it's so nice. Superb work, Mr. Maxim. Yeah, oh, look at the tips. They look so nice. And the realistic temperatures. Do we have a drilling here? Yes, but with the SPH, I think. This is his website, I think. Ilyushkin Maxim Valerievich. Let's not pretend that I know what it means. I know how to read broken Russian. Вы можете заполнив поле обратной связи написать письмо на email. Right. What city is Михайлова? Нет. Ульяновский, нет. Михайлова. Основной and инженерный центр. I'm curious to see the address. I'm curious to see where is it possible? No, I don't think it's possible. I think this is the city, Ulyanovsk. Город is city, huh? Ulyanovsk, Russia. So this is below Kazan, near the, it's on the Volga River. Do we have something? Yeah, yes. Молоко, this is milk. Магазин молоко. Составление договоров. Консультация. What is here? A factory, I think. Or some offices. Nice to see you, Mr. Maxim. You're doing awesome stuff. Oh my God, oh my God. This is a SPH, yes? If it loads. No. This is what? No, it doesn't load. Maybe it takes some time to load. This is airplane on SPH or on soil. on floor. I mean, there is no SPH. It's not nice breaking. Yeah, very nice. Let me subscribe to Mr. I'm already subscribed. Okay. Yeah, very nice things. Let me like more because I'd like to. I hope it's not interfering with the live stream. 7 minutes. So yeah, it keeps inclined in an optimal manner, the tool. Yes, nice work from Mr. Maxim. We have 3 hours. Our additional message. What is this? Yuri Novozhelov, I think, another Russian engineer. Nice waves, yes. Ooh, I think I can do some waves like this. Yes, I can do some waves. Yeah, it's just moving the wall. Yeah, I'd like to perform something similar. Let me write this down. Yes. To work. Learn with crazy engineers. Popular mechanics. This is nice, only it's not advancing. It's not going downwards. It's not. It's nice for this first layer. For this shading, it looks awesome. It's very nice. Nirvana. Mr. Yuri Novozhelov. Yeah, nice. Nice work. Does he have more? Only this? Crack growth estimation is done. Let's see. he's only showing results. Okay. This is very nice, and it's not easy to perform fracture mechanics in LS-DYNA. It's not easy. On the results, yes. It's just moving the hit point. Yeah, gradually I think we are approaching the end of this stream. Let's wait 4 more minutes, then we can close. ANSYS meshing in parallel. Four million nodes, and he has parameterized. He made the parameter out of the element nodes, out of the element count. All right. Orthogonal cutting process. The temperature is a little too high, the temperature, but you know, crazy engineers. Let's see what they have. LS-DYNA tutorials, LaTeX, MATLAB. How to save high quality image in Abacus. You hit the print screen button. This is all. Will it break? This is the question. Come on, maybe show stress. All right, yes. Plastic strain. So, no necking? No necking, huh? No breaking? No breaking, no necking. It might be that the material was not correctly assigned. We don't know. Crazy engineers. I will leave you with this simulation, which is very hard to make. So it's pretty basic, let's say, but it's very hard to make the drilling simulation. Very hard to make. In ANSYS Workbench, of course. We simplified everything. I mean, I let only the useful portion of the model, so yeah, I simplified everything, and this is what I obtained. Almost 1 minute. A quick reminder of the, let's say, the submerged milling while the process is being submerged in water. and you can see the chips traversing the water. You can see here, for example, this is the cavity that it followed. Here it forms a cavity. Here, this cavity. It's a little too fast for the solver to create a cavity, you know, between the chips, around the chips. And also the model is rigid, and this is why we don't have a clear tightness. For example, here it's not a clear bubble in the water because it's a solid model. If it would have been a shell body, then we would have had a nice bubble around the chips, but we cannot have shell bodies in principle in a machining simulation. Yeah, only the tool can be shell, not the workpiece. It makes no sense to have the workpiece as a shell. So, with God's help, we successfully finished the simulation, and let's see. So we are there where we should be. It looks very nice. Why do I have such? I let the mill as linear and not nonlinear. So I advise for the people wanting to do their own simulation to make it structures still nonlinear. This is why we have such big stress value, let's say. So yeah, it looks so nice. Let me also show you temperature. Click Solution, Worksheet, and below here, below, we have temperature. Look here, temperature all. Right-click, Create User-Defined Result. Right-click, Evaluate All Results. And now we have some temperature. Yeah, it is some temperature. It's not the perfect amount. I would have liked to have even higher values. Also remember we have a section here. Yeah, it's a nice role for a basic lecture, let's say, for beginners. It's a nice start. So thank you very much for the audience for having the patience to watch this presentation, this live stream, and all the best to everyone. Thank you and bye-bye.